Right. Good afternoon. I hope you are all well. Thanks for joining for our lecture this week on EG-M37. I'm just going to check some of the systems are working. So I've launched a poll there with some just basic questions, which I'd be happy if you could have a go at while we're going on. Hopefully it won't take too much room on our Zoom. What we are going to look into today is a topic which is not examinable. So this is one of the non-critical lectures which we left off last week and left until the very end. We'll go through this relatively quickly. There's a few ways that we can interact here. So obviously I've put the poll up to find out, make sure you can all hear me. No one said no. And on the your participant screen, you can also, there are some ways of answering if you can want me to go faster or slower. For example, there's a chat as well, which I will launch now. Here we go. So there's a chat screen. Hello, everybody. Like so, and you're welcome to ask any questions as we go along there. I'm going to go very slowly. I like today to be more of a chance, really, just to catch up with everyone. Obviously, I'm going to talk a little bit about the simulation side of additive manufacturing. But I'm going to try to finish early, and then we can just have a general chat about your project work or tests or any questions you would like to discuss about the module. We'll do at the end. So I'll just bring up the chat again. So is everybody happy with this? And can you hear? Okay. Something to nice one. Yes and yes, brilliant. Good. Good. Okay, good. All right. Well, this would have been our lecture 16 had our industrial lecturers also joined in. I'll come back to the polls later on, and we'll do I'll open up the floor a bit for questions and comments in a bit. This is all about simulation. So basically, additive, I'm going to sort of deal with the questions of why model. Then a little bit, we've been through in the physics of modeling, we've seen the complexities. So we're going to introduce those complexities, and then on that basis, we're still going to ask the question of, again, why model? And I've kind of approached the computational modeling from a number of different aspects and size scales, time scales. So we'll go from thermal modeling, which seems to be probably the most predominant around additive, basically powder melting acidification. And if you like modeling, this is probably the funnest thing to do. But we will deal with the thermal modeling all the way from, we will look at some examples of thermal modeling all the way from large scale components right the way down to the powder melting. We'll talk a bit about residual stress prediction, and then issues that evolve from the multi-scale modeling. and how these can be used to optimize the component. And we'll talk a little bit about the future directions in modeling. So just to sort of say a little bit about where we are with them with the module at the moment. So this is what I would say is just a an interesting area of additive, and it's a non-examinable chapter of what we're doing. We've got essentially 4 possible online slots in the next 2 weeks, which would cover a normal term. Now, this is far from being a normal term, but I'm aiming to try to finish by the end of the 3rd of April, which is what we plan to do, and have the next 4 slots online. This one, I was just going to talk about the finish off the last chapter with the simulation, and then we'll have 3 open slots. I am trying to get to see if I can have one of these given to you by one of our industrial speakers, but to do it online. So maybe Colin Cater had a very good presentation ready, which I've had to look at, and hopefully he might be able to give it maybe tomorrow or next week. But then I was going to reserve 2 of them a little bit for sort of like a revision of questions, just to kind of focus on the type of questions that might get asked in an exam. Okay, so moving on. So why should we model at all? Well, the different applications of the modeling. So we can use modeling to modulate, to simulate the process. And one of the things why simulation at a small scale is very handy is because we are unable to see what's really going on with the naked eye. It gives us an understanding of better understanding of the interaction of the different physics, and it gives us an understanding of at a very small scale, for example, of why materials behave and solidify in a certain way, which we would never have the option to the understanding of without the modeling. Obviously, mathematics on its own is not strong enough, and the empirical doesn't give us enough of an insight. Then at the level of the component, we can also model, and this is where we would use finite element analysis linked with optimization to come up with shape optimization, and then components which very much specifically optimized for a given loading. And these are now almost an integral part of CAD, coming from the CAD side, with things like Autodesk Fusion 360, which is I've been playing with over the last few days. It's incredibly interesting and very powerful. But then, of course, this is more mainstream, integrated within ANSYS now. Altair, OptiStrat, and a number of different ones. So this component optimization leads to geometries which could not be made in any other way, and have multiple functions built into them. So they could be integrating sort of a lightweight structural design with a sort of specific strength which is unachievable, that would not be manufacturable in any other way. You could also integrate lattices for functions such as heat transfer or electromagnetics, or so a wide range of components which we've not even touched on in terms of what could be achieved. And really, the main thing about modeling is that because of additive manufacturing being what it is, a computational driven, highly flexible, with a huge degree of freedom, we have the ultimate sort of goal of all of this is to integrate the virtual designer components from start to scratch, with that very amazing goal that you could actually design and then finally print your components without any sort of trial and error production steps. Now, we're a long way from that, but we are always evolving towards that, and the computational modeling really helps towards that. So Why? As I said through this, no simple engineering calculations, no basic sort of mathematical equations which represented. It's at the moment the operating on the machine is based upon experience. So a lot of the pragmaticness of setting up a build depends a lot upon the operator and the experience of the operator. So all of this, without the modeling, means that there's still a cost component involved in being able to get a successful component run. And so modeling and understanding will help to reduce these costs eventually. And as I said, this multiple functionality, such as the reduction in weight without a strength penalty, is something which you know, is obviously an amazing thing to be able to do. Now, it is difficult because through the physics we have this rapid, very rapid cooling rate, and it's affected by a number of different things on a number of different scales. I've said already where additive manufacturing sat on the cooling rate spectrum, and this is a particularly difficult combination of length scales and so these are real time imaging. So now all of these different systems work on different scales with different lasers. So this is a lot of change going on. When we look at these systems, obviously the lasers are fast moving. And then when you actually zoom in with a high speed camera and to capture some of the physics of what's going on, you actually find that it's even more complicated than you thought. It's a very explosive process. So see here on the left, you can see there's a very high frame rate image capturing with lots of the ejaculates and soot and melt pool is a highly volatile, sort of very explosive environment. It is obviously doing the job, but being able to explain how it's doing that job is a degree harder than what we see on normal welding scales. So in these very small welding scales, particularly with the powder as a feedstock, this explosiveness makes it very difficult to model. So just to reiterate the physics and the scales, so we've got the main heat source, say this could be a laser beam, but we can also talk about electron beam in the same sort of context. We have the interaction between the powder bed and the laser comes through the medium of a thermal radiation, which is obviously driven by properties such as absorption and reflection of powders, and these are temperature dependent. In terms of flow, we've got convection and we've got a forced convection. Gas is going over the top of it. During this interaction between the laser and the radiative source, we've got both vaporization and condensing happening within this gas flow, which carries away small plumes. We've got melting and solidification at the powder. So this part in the powder bed with the monocyte powders is an actual simulation. So you can see the thermal contours underneath where the laser has traveled, going through the contact points of the powders, and you can see that there is effectively a conduction through the powder down onto the substrate. And you can see the melting and solidification, and at the same time you then get shrinkage. So as I said, you've got conduction. When you've got conduction, you've got sintering at neck points, and you can see that sintering happening here in the powder particles. And within the melt pool, this point here, where we've still got a high enough temperature that you've got a molten liquid of metal, there are potentially capillary flows on this small scale. Remember, these particles are only of the order of the same size as the spot size, typically about 70 is the spot size. So the particles themselves will have an average size about half that, 35 microns, maybe 40 microns. And at that sort of size, a lot of the sort of capillary flows, the wettability and the surface tension leads to a different type of convection cell within the melt pool. And then we've got the discrete nature of the powders as it tumbles down from the hopper and is spread across the plate with rigid body movements of the wiper. This causes a segregation of particles. Typically small ones go to the bottom and larger particles rise to the top as they're driven across. So it's almost counterintuitive, but this will cause a segregation of particle sizes, which itself will then have an effect on things like porosity. So there's a lot of physics going on, and it's on a lot of different scales. So you've got everything from down at the certification scale, you've got evaporation at the atomistic scale, you've got melting at the micro scale, you've got interaction with the laser at the micro scale, you've got powder flowing over at sort of micro to macro, filling a sort of 50 micron layer bed, and then you've got the macro scale of the plate itself and the gas flows on the macro scale, and then you've got the size of the component can be all the way up to 250 millimeters again, so that's what we would say on the macro scale. So this is partly how the models which we're using in additive tend to get divided into. They'll get divided into models which are working down at the micro scale at the level of the powder. And these are handy for trying to understand things like defects, melt pool instabilities, and the influence of powder size distributions on the models. Then we've got, and these will be in the order of micrometers, microns, and typical types of methods that we use, a combination here of Lattice-Boltzmann methods, discrete element methods, and computational fluid dynamics down to that level. We then step up a size, so this is what we might call the hatch model. So we're able to capture hatch patterns, and you can see one of the models here that's been developed at Swansea University, which is a finite difference-based three-dimensional model. You can see part of a square checkerboard. Here's some temperature. This will typically predict local temperatures and might be coupled with some sort of stress analysis to give you local residual stresses as they form. Ultimately, these will all feed in at some point into some sort of layer model, something up in the sort of centimeter. And here you can see a turbine blade between section with some support structures underneath. And ultimately, the models are the layer models want to take some of the information from both of the micro and the hatching models and feed them into the layer model, so that we have maybe things like residual stresses and maybe some defects, not everywhere modeled, but sufficient to be able to just give you some idea of the ultimate thermal history in the part, and therefore also residual stresses in the part, and maybe to be able to do these quick enough so that we can optimize the layout of the support structures. But just to put this in context and the type of computational power that we need, these models, these powder models, are the smallest scales of micrometers. To be able to simulate that through to a realistic length scale, so maybe 1 or 2 millimeters, can take up to a week's time on a high performance cluster. As we go up the length scales, the models become much more pragmatic, but then so do the sort of size of the models that we want to look at. So if we wanted to look at an entire cross section, and this here being representative of maybe a sort of 10 millimeter patch, then we might end up looking again at 5 to a week simulation runtime on a high performance cluster to be able to capture a few layers, 4 or 5 layers of a proper component cross section. These large scale, the larger scale models, the layer models, these could take anything of the order of a couple of hours up to a few days. But the whole idea of this, and it does integrate and becomes significantly faster for companies to be able to run the simulation within a week for the entire component. Right, so here are some examples of simulations which you can see going through. Now, Often, as is the way with multi-scale modeling, it isn't only done on one set of models, it is done on a variety of different models. And you can see how here on the top left and right, we've got simulations using Lattice-Boltzmann, which are developed at Swansea University. FLUENT, which you all know exists within ANSYS, has some very powerful multi-physics simulation capabilities. And you can see, for example, here, a square patch of powder being melted, and the type of convection cells that you get within it based upon Marangoni convection. So you can see temperature on the left, and you can see the bead forming, and you can see the melt going underneath. With the same capabilities in FLUENT in 3D, you can see the laser traveling on, melt behind it, and the powder particles being sort of melted behind it and along the track. Another code which has been developed at Swansea University, the discrete element method by Professor Steve Brown and Mark Holmes. You can see how powders of different sizes have been colorized and being spread behind a wiper, or sorry, in front of the wiper as the wiper goes over. And you can, this has been integrated now into a code by EOS-EADS. You can see here another finite difference, another code developed at Swansea University of just a finite difference for a block with a sort of meander pattern laying down some a laser pattern along the top of the block. Another example of FLUENT here, where you can see flow happening in the air. You can see a melt pool. You can see powder particles being melted into each other. And then this at the top right here is a stress simulation of an additive part with porosity in it, looking at how the porosity acts as a stress concentration point, which then leads to paths of plastic failure that can link up and weaken the part. Okay, so those are the different types of models which just a number of different models which have been used here at Swansea University. But now if we start looking back at the history of modeling over the past sort of 20 odd years, if you're interested in this, in the modeling aspects, then I suggest you can find a review paper of ours, and you can find that on my website, which reviews all of the SFF, which is the Solid Freeform Fabrication Conference, which has been run every August since 1991, and it's so you can track the history and the development of additive manufacturing through the papers which are presented at this conference. And I've specifically picked out some which are to do with modeling, and it quite nicely shows sort of an increasing level of capability of modeling, of complexity of modeling, and then you can also see a lot of the most current sort of platforms such as electron beam coming in at specific points throughout the development of these. Some of the most interesting ones are obviously coming now in the sort of late 2010 onwards, where you get papers by Caroline Corner, and you've got papers by Brent Stucker as well. If we look at some of the simulations, which you can actually do these in FLUENT, and you can show here, this is on a larger scale, and it's just to show that what happens when you have capillary convection with a laser. This is the larger laser coming down onto what is effectively like an aluminium solid surface. There's no powder. And you can see the development of this of the melt pool. So you see vectors, you can see temperatures, so you can see the temperature and of the higher temperatures underneath the laser as it melts. And you can see here the convection going in a clockwise manner. Now, this is driven completely in the modeling by the surface tension at the interface between the solid and the liquid. And this surface tension causes a flow in this direction, which actually causes a wider rather than a narrower melt pool to develop underneath the So you can see the melting point is coming out. This is actually going to go wider than the diameter of the spot coming down on it. If what would have happened? I know this is a question. What would have happened if the melt pool, if the surface tension had caused the melt pool to go in the other direction? So let's put that out there as a question. Okay. What would have happened if the recirculation, the melt pool, had been anti-clockwise instead clockwise? Sorry, that's a question. Right. Anybody? You can put a private. Okay. What would? From me. Sorry. That's my question. Hang on. Let me just put that out as a general question to everybody. What would have happened if the recirculation of the melt pool had been clockwise instead of anti-clockwise? So what you can see here is you've got a clockwise melt coming down past, here's the solid interface, and then coming back up the middle. Ever think about that? What would have happened? What would have happened to the melt pool itself? I have mentioned it before. Anybody want to? You can send me a private. Yes, we're on the right track, JC. Yes, it would have become elongated. In which direction would it have become elongated? Downwards, correct. Absolutely, yeah. So if the melt pool had gone in the other direction, okay. So say if we'd had this convection cell coming up back into the laser, yeah, then it would have come back and then transported heat down the middle line, center line, towards the bottom of the to the bottom of the melt pool, and it would have become elongated. So the melt pool would have become, anybody? No, it's not just keyholing. It looks like keyholing, but it's not. But I'll come along to that now. So the melt pool would have become deeper. Okay, you would have had an elongated melt pool. It isn't keyholing. Keyholing happens when you get evaporation happening in the center of the top, and as that evaporate forms, you get a plasma forming, and the radiation comes into the plasma, through the plasma, and gets reflected off the sides back into the plasma, and you get an acceleration of the, you get like a boring effect. So that plasma actually bores down, and your keyhole is much deeper yet again. Okay, so what I'm talking about here is the aspect ratio. If we take the width to the depth, will become distorted or will be changed by the Marangoni convection cells. Okay, so another question. Okay, if in this case we've got we've got a clockwise movement of the convection cell, and we've already established that if that was anti-clockwise, it would go deeper. What could cause a difference in the direction? What can cause a change in the direction in the convection, Marangoni convection cell direction? Yes. So yes, it is. It's a temperature gradient, impurities. Thank you. Well done, Matt. Yeah, good. That's right. So, and this is the example that I gave you a couple of weeks ago, where potentially small impurities in the composition of 316 steel particularly the sulfur, are known to go through a very small threshold in parts per million, where if it goes above a certain amount, the Marangoni convection will go differently. And this is seen, this is actually a phenomenon. This example that I'm showing you here is a welding phenomena, which also happens in laser powder bed fusion, but you can see it on a larger scale, so you can actually see it by eye when you're doing welding with larger scale welds. And yeah, so when looking at 316, if you have those impurities in, you will get possibly a deeper or shallower melt pool. Anyway, that's something which I think is very interesting, but this is something which explains to you at all levels with the modeling, explains to you why that happens. So this is just showing another simulation, this is actually done in FLUENT again as well. This is on a smaller scale now, at the size of a powder, and you can see a sort of square blob of powder being melted in such a way, and this is the convection that happens again. All of this is Marangoni driven, and you've got this hot spot on the top here, and you've got, and if you look at what actually a bead of a track of powder, a single track of powder looks like when it's been melted with a small amount of penetration, and you've got some very obvious similarities with this domed forming on the top. Okay, so this is the very first simulation that I showed you, and again this is another FLUENT simulation, and you can see it just repeating over and over. This has been done again for another sort of aluminium type powder with a low melting temperature point, simply more than anything just to go for the simulation. You can see the radiation on the very last instance where there's no powder there, heating the base plate. And this can all be done using sort of some of the radiative models which are in FLUENT. Sometimes you can read a bit too much into modeling, but this one is very interesting, I think, to a certain extent, because you've got gas flow. You can see the gas shooting out between particles which are close together, so there's quite enough higher temperature movement of gas close to that. What you don't really get, and I think this is a deficiency of many of them kind of models down at this scale, is that you tend to see it's a bit static, and in reality we know that there's a lot more movement in the powder particles. So as the laser comes along, these particles, there's a lot more dynamic particles are coming in, moving around, and sometimes being thrown out much more in a much more volatile manner. But still, it does allow us to capture some of the physics. And if you read it and too much into the modeling, you can start to see all sorts of things happening which you think you can explain, such as balling happening behind. You can see the formation of satellites and larger particles being thrown off. So lots of different things. Certainly at the end of it, though, parts that haven't been melted, you can see porosities that have been left behind from the lack of melting, and then you can see porosities that have kind of formed by the gas entrained this spherical porosity. So a lot of things that you can look at the model and sort of try to explain. Powder simulations tend to be done in a very different way. So most of what we talked about there was using continuum-based fluid dynamics on the basis of solution of partial differential equations. So the simulation of the movement of powders is often done by using the Newton's dynamic laws for single particles. And putting enough of them together, you can get a statistical, a meaningful solution, which allows you to interpret how the particles will settle down together. These are meant to be some simulations and animations. You can see a wiper coming across and spreading some powder along the powder bed. Once that's been done, you can couple continuum-based models and discrete-based models. This is a type of modeling called Lattice-Boltzmann, which is very interesting because it uses it's meshless to a certain extent. So and it uses a sort of Monte Carlo style solution on a statistical equation, the Lattice-Boltzmann equation. But in this case, what you can see is being done in the model is that a discrete model has been used to spread a powder with a sort of set of distributions, and you can see the laser moving from bottom left to top right. And in this simulation, this is by Professor Steve Brown, you can see that he has allowed some particles to move in from the side, and this is being done more and more at the moment by in different places across the world. So this is done by Lawrence Livermore, and I've shown you this one before. It actually shows the capture of balling happening. So with a lower laser power, it's able to explain why it is that you don't get a complete fusion track, as you have on the bottom one. Has got sufficient power to melt a track, and you can see what is a sort of effectively a relatively straight track forming on top of the powder, whereas on the top one, where there's not quite, it's been moving too fast, there isn't quite enough laser power, you get this balling behind the track, and that's what happens below, is when it's not completely fusing properly. Here are a couple of simulations. This is using Lattice-Boltzmann with and without Marangoni convection. So you can see that with the Marangoni convection, you've got a slightly larger melt pool, and it's working on exactly the same sort of background grid. Anyway, all a lot of fun. We can keep on watching that, but I want to push on a bit. So, as a result from that last type of simulation of a Lattice-Boltzmann, we were able to get a predictive relative density. So you can see that it is catching a sort of densification curve. So there is some sort of correlation between the melted and unmelted porosity. So this type of densification we've got here. There's still a lot more to be done on that, but you can see the relationship is at play there. These are the type of equations, though, on the Hatch model. Typically, again, solving the Fourier heat equation, which we've seen a few times, with a Gaussian distribution given for the laser power. And here's simulation in action. And you can see here, for example, a meander hatch pattern on the top of a substrate. Material properties are always the downfall of most models, and here we can see some typical properties which are used. We'll need density, specific heat, liquidus, solidus, latent heat, thermal, and a lot of these we have for solids, but sometimes it's more difficult to get hold of them for powders, and certainly even harder then to find those as a sort of temperature dependent. So if we just look at that last one, you can see here we've got some data for 316 we've measured ourselves, and we've got the thermal conductivity of both the powder and the solid there. One of the things that you can use the hatch layer model is to actually look at different type of hatch patterns. So here we're using a number of different zones. We're using a number of different directions in which the laser travels. So you can see here, for example, I'll set them all off at once. You can see the sort of thing that you can do via simulation. Bear in mind these are all three-dimensional. So you can see stripes, you can see meander, you can see 4 zones with meander, and then we go up to 16 different zones, there, meander and stripes, and so on. You know, the combinations are endless. The sort of thing that we can do is obviously then we can average the temperatures in these different zones, and we can look at trying to even out the temperatures in the peak and lower, higher temperatures in all the different zones. when we start putting all these temperatures together from all the different types of hatch patterns, we can see why it is that some of these give us high peaks and troughs, and others give us, like the 16 sort of checkerboarding pattern over the same zone, gives us slightly lower peaks and troughs, but maybe a slightly higher average. But the net effect of some of this could be then to reduce the residual stress. So, I mean, that sort of modelling at the level of the melt pool is something that we've done a lot at Swansea. Here gives you some of this. This gives you an example of the development of keyhole and how a keyhole develops. So that there is what a keyhole melt pool looks like, Chris. And you can see the top-down tracks, and here's some modelling of the keyhole as it develops. So it gives us that connection between the thermal and the residual stresses, and it gives us an understanding of how different hatch patterns can avoid them. Now, one of the most difficult things is that we can't actually validate this using thermocouples, because the timescales and the temperatures are too high and the timescales too small. So we have to rely upon our models. I'm only going to go through this very quickly just to show you another application of modeling in additive. This is about improving the. So one of the link has been made between the gas flow and the importance of the gas flow through the machines. So again, that's something which modeling has helped to optimize the jets. And Dan, who has been working with you on your projects in the practical room on every Thursday until a couple of weeks ago, he's doing his engineering doctorate on gas flow. So what you can see here on the right-hand side is a paper by Chris Sutcliffe's group on the flow effects on mechanical properties. And you can see here the simulation. You can see the simulation of the flow and the flow rates, and also measurements of porosity on the, so you've got the porosity on the left-hand side, and you see the flow rate on the right-hand side as measured 10 millimeters off the substrate. And you can see how they have correlated. So these cylinders, the little round circles here represent little cylinders for mechanical testing, and also to measure the porosity. And you can see the areas of higher porosity match the areas of lower airflow. Gas flow, I should say, because it's argon. And so from that point onwards, they decided to look at use computational flow dynamics to understand and then optimize the nozzles. And this is part of the work that is ongoing, part of Dan's work. You can see here a typical internal CAD of the SLM machine. So you've got the theta lens on the top where the laser comes down through. You've got the base plate at the bottom there, and then you've got an inlet and you've got an outlet. And the inlet itself is made up of a manifold which splits into 13 smaller inlets, which jet across the substrate, and then you've got a big outlet for on the left-hand side. Now, this is an old machine, one which was optimized. Obviously, we need some flow properties for the argon, so we've got density, viscosity, some Reynolds, typical Reynolds numbers in the order of about 3,000 or 4,000, so turbulent, but transitional turbulent. And here are some simulations. On the left-hand side is the measurement, the experimental measurement, and here are a bunch of different turbulence models which we used. And you can see here that they don't all match perfectly, but through a combination of changing the model parameters, we were able to fine-tune to the point where the you can see a relatively good correlation between this turbulence model here and the hot wire anemometry on the left-hand side. And you can use that, and it shows you how you get hot spots on the bed, and this was used to eventually So you can see here very clearly a recirculation on the bed, and this is going to lead to differences in porosity, and we know that that does happen, and we have been able to correlate it with the gas. Just another example of how CFD is used. We can also do, if you look at, if you pass a laser on a plate, this is an ANSYS simulation where you've got temperature on the top and then you've got stress analysis on the bottom, and you can see the two running side by side. So that again is something where we look at predicting, and this is now sort of more on the macro scale. You can predict the residual stresses, and you can use ANSYS in that mode in Workbench, or you can use ANSYS with APDL and to predict residual stresses. All of these simulations can be linked in together, and one of the things which is really coming along in the last couple of years has been topological optimization. So with tools like Altair, OptiStrat, but even Autodesk bringing in its own Fusion 360, which is freely available for student use, and then also ANSYS Workbench itself with Space Claim. This is the virtual loop of design, which is so particularly interesting, and this is where we're seeing this has been applied. Again, work done here at Swansea University, where we've applied it to a number of different load cases can be optimized at the same time. This was for the GE engine bracket, and this was a almost like a sort of crowd-funded project, not a crowd-funded project, sorry, an open project, which open challenge which GE put out to redesign this bracket to be made additively. And you can see this is the typical loop which an optimization loop goes through. So we'll have a design space or an initial component that will have a series of constraints, loadings and constraints, and maybe some material constraints, and the whole goal of this is to be able to make it additive. So we put it through a preliminary stress analysis that allows us then some sort of topological optimization, which will be done on a minimization of mass or volume, and from that we can pull back in a new design, which is then reanalyzed, which will be lighter. Now the tricky bit here is to actually incorporate lessons learned from additive, so that we know build orientations, and then knowing some of the material properties which are a result of the manufacturing process. These need to come back in again, so the optimization is done almost a second time with real material properties and constraints from additive. This can be done multiple times to be able to come up with components which couldn't be made another way, and have an integration of they reduce the weight, they have a higher specific strength, and they have incorporated the entire manufacturing sequence. It is the last few steps where the integration of defects of porosity which occurred during the manufacturing. This is probably the weakest link, and it's the part that needs to be worked on over the next few years for additive to become truly accepted. When that happens, or even possibly before that happens, there are many other designs which are going ahead, which are less critical than engine brackets on aircraft, such as this conformal cooling example, which was done by a bunch of students from you on your course, Nicklin, Rees, and Latham, a few years ago. They worked on a conformal cooling channel, and they looked at the design. So this was the MSc project with Dr. Andrew Rees. And yeah, this was an integration of ANSYS simulation and repeated build plate and build simulate optimization. So I would say that in terms of modeling has moved incredibly quickly over the last couple of years. ANSYS has come up with its own, has integrated an American effort by Sims and that is available now within Workbench. ESI-AM software has become commercially available, and Autodesk have introduced the Fusion 360, and a lot of the optimization efforts are now there. So all of these things seem to be converging much faster than predicted, but we still have quite a few steps to go with the modeling. It is still very slow, and the material properties for the models are still far from being very complete. So that takes me through to the end of the lecture. So what I wanted to do now was have a look at, oops, somebody couldn't hear me and I've ignored them. I hope you're able to catch up on that. Not to worry if you haven't, this is all being recorded, so I'll be putting this up on Blackboard later tonight. Let me just get the chat up as well. What's the difference between the uni and, oh, sorry, JC, I missed your question. I think uni is unidirectional and B is bidirectional. Just answer that question. Sorry, got carried away there. Right, so only half of you have got all the way through your tests. Okay, I've heard a couple of people have had problems with the test C24. I went to check on it this morning and I had no problems running it. So has anyone here had problems with C24? So I would urge you, we've got, I think the deadline for the C2 tests is the 27th of March. So try to get them done if you can before then. So 70% of you here have finished your design for C1, and sort of about half of you that have finished have uploaded your files to Blackboard without a problem. Okay, so I know where to go to find them. I should say, can you please email me to let me know when you have uploaded your files, please. Okay. All right, then just a quick update. So I hope you're all keeping well and made it home. If you have gone home, made it home safely, and everyone's family's fine. The university is in shutdown at the moment, so as of Friday, our buildings were locked, our labs were locked. So we are at present completely unable, and this is something which I had been kind of expecting or dreading, but it's happened. At the moment, if it carries on like this, we're not going to be able to print out your parts. Now, I'd like to suggest to everybody here today now that you focus on C1. We may give you a slight extension to the deadline, and I'd like to for each group to think carefully about how they can, even if we don't print and we carry on online, do your absolute best on C1. And this may become a bit clearer later on. It might be a very important demonstration of the work you do on this group. Okay, I'll check that. Okay, so can I just, yeah, I'm just going to reiterate that point. Yeah. So again, if you can spread the word, at the moment there's not too many of us here, only 10. but for your group members and others, can you please, you've got plenty of time till the end of this. I'm going to start sort of hinting it might be worth putting a little bit more effort into C1 than you might have thought otherwise for 20% of the module. Okay, that's what I'm going to say for now. But if you can, yeah, by all means, email me. But I think you know what the design brief was, and I think it's just when it comes to doing the write-up, I think it's worthwhile putting in the extra. Yes, absolutely. That is that's something which we can do, Chris. And do you have a suggestion how many more pages you might want to put in? I think it was currently 8 pages. Was that right, or 10? Sorry, just off the top of my head, I can't remember. I've got 2 modules going on. Does anybody remind me what it was? What was the page limit on the Chris? Okay. All right. Yeah. I'm going to have to think a little bit about how, but we have got sort of, even the deadline before was the 1st of May, which I think with everything it is as it is at the moment, I don't think it's going to be, it's not the deadline that we should be worried about. It's how this all fits in anyway with what's going to go online. But yes, I think it will be a bit longer and it's going to be a little bit weightier. And I think that that's why I'm suggesting put a little bit. Whereas before I was saying don't put too much effort in. Now I'm saying is put a bit of effort into this and finish it off nicely. If you have submitted files and you think you want to go back to have another look at them, that's fine with me as well. So as we're not, it's very unlikely we're going to be able to print it, which is a gutner. But I have no control on that. If it does happen that we get to go back into the university and Dan gets some time in the labs, then I will try to obviously print out the parts that have been submitted to me. Okay, so what should we do? That is what I need to decide. So for the time being, it won't be anything. So so it won't be anything that you haven't done already. It's just maybe going to a bit more depth about, I don't know, laser powder bed fusion, how it been made, a couple more references than you would have done. There some more pretty pictures. Yeah, that's fine as well. It's not going to be massively onerous, honestly. I'm not going to make you do loads more work, but I would like to. It does have to be, I think, a little bit more. Hopefully I'll explain a bit more of that in the future. Yeah. Okay, so keep safe and I'll see you tomorrow. So unless any other questions, quickly. No? Okay, well, glad to see you all. And all right, thanks, Chris. Tell that to the head of college. All right. All right, guys. All the I'll talk to you soon now. Okay, bye.